Thanks, everyone. As I said, those who wouldn't know me, I'm Pieter Wuille. I've been working on Bitcoin Core for a while. Well, this is work I've been doing at Blockstream. So today I'll be talking about key tree signatures, which is what I've been working on the past few weeks. It's basically an improvement to the multisig schemes that Bitcoin and we want to support. So this is an outline of my talk. I'll first talk a bit about multisig support in Bitcoin, K of N thresholding. I'll go into that better later. Then I'll talk about what if we restrict the problem to just one of N and see if we can improve that. Then alternatively look what if we want just K of K, where everyone's a signer, and improve that. Combine the two approaches to get something which gives us a better K of N. Then generalize this into something I've been calling threshold trees, and then finally talk about some future work. Okay, so K of N in Bitcoin. So multisig. This is basically the mechanism where you have, for those who wouldn't know it, you have signatures transactions that need to be signed by several keys in order to unlock some funds. There are different use cases for this. So one of them is multi-device security, where I create a transaction on my laptop, but I'm not quite sure about the security of the system, so I'd like to require a signature by my phone as well. So an attacker would need to both compromise my phone and my computer. Another reason for doing this is a low trust escrow. So you can do, if you require 2 of 3 signatures, one of them is the sender, one of them is the receiver, and a third is an escrow service, which gets to sign off on who gets the fund, whether the goods were delivered or not. And this is an improvement over the traditional escrow system where the escrow just gets the money and can run off with it. So this is an escrow that gets to decide who gets the money but doesn't have it themselves. And of course, whenever you have shared funds, some company holds money that not just a single person should be required to unlock them. So in Bitcoin, this is implemented using opcheck multisig, which gives N public keys and requires K signatures with it, where K is between 1 and N. Though in Bitcoin, N in this case is in practice limited to 15 keys due to the restrictions of P2SH, pay-to-script hash addresses. And it has a downside that the validation performance, if such a check multisig transaction is being used on the blockchain, its validation performance depends on the number of keys. So if you do even a 1 of 15 multisig, it can require up to 15 signature checks that everyone in the Bitcoin network will have to do. So this is a resource constraint, which is not nice. And so the storage size, you need to publish the full public keys and signatures into the blockchain. So this is linear in K and N. So this means that even if the restriction of these 15 keys were limited, there is really no way of doing thousands of keys involved. The transactions would be huge. So Gregory Maxwell a while ago, and this should show a video, but it doesn't, came up with a number of interesting properties that this sort of signature schemes can have. So we called it ACE up, accountability, composability, efficiency, usability, and privacy. So I'll go over these properties for check multisig in Bitcoin. At the end of the talk, I'll refer back to them with the new scheme we've constructed. So accountability is the ability to see who signed off to spend the funds. If you have a 1 of 10 signature scheme where anyone in a company can spend the money and suddenly the money disappears, you probably want to know who spent it. Composability is, if I have a multisig, someone, you want to receive money from me, but you would like me to send funds not directly to a single key of yours, but to such a multisig scheme. Now I want to create a more complex transaction that either pays to you with your already multisig or to someone else. Can I construct a can I improve the scheme and combine the two? So this is something that the traditional Bitcoin multisig cannot do. You cannot do 2 of 3 or another 2 of 3. It has to be represented as a single. The efficiency, as I said, it's linear in K and N, which is not very good. Usability is pretty nice in check multisig. Someone creates a transaction, broadcasts it to creates it without signing it, broadcasts it to everyone, everybody signs it, you bring the partially signed transactions together, and the result is a fully valid transaction. So it only needs one round. And then there's the privacy. This is something where check multisig is really bad. Everyone can see all the public keys involved. They can see what the actual policy is. So you cannot hide the fact that you are using a 5 of 8, and maybe it's known that you are the only real user of 5 of 8 keys in Bitcoin. Well, then now everybody knows it's you. So let's talk about how we could potentially improve this. First of all, let's restrict the problem to just 1 of n. If we think about what is a 1 of n multisig scheme, all you need to do here is have a set of public keys, choose one of them, create a signature with it, and then prove to the blockchain or your consensus system that the key you used was part of this set. Now, there exists a solution, it's already being deployed within Bitcoin, to prove membership of a set. It's called a Merkle tree. So in Bitcoin, it's used for SPV nodes to prove to SPV nodes that a particular transaction is part of a block. So I'll talk a bit about Merkle trees. The idea is here you start with a bunch of leaves, in this case keys. You take their hashes and you combine them pairwise to produce a higher layer of of hashes. So you start with a layer of 8 possibilities, combine 2 of them together into the hash of both. This results in 4 hashes. Then you take 2 of them together to produce 2 hashes again, and then you combine those again together to create a root hash. And anyone can then prove membership of this root, and I'm going to show you how. So this is a program in pseudo Python style coding so the question is, given a root and a leaf, prove to me that that leaf is actually part of the set that was hashed to construct this root. So X is the leaf in this code. It takes as input 3 booleans to determine which direction we are going up, and 3 hashes which are being combined with. So I'll go over it. Say we want to prove that K4 is part of the root. So I publish K4. I also publish K3, and a boolean to say that K4 is the second here. So you combine those 2 together to recompute D. Then I also give you C and say that it's left of it, hash those together to produce A. Then I also publish B and say it's on the right of it, to hash them together and it's the root, and then you verify that this root matches. So what you can see is this is actually 3 times the same step we're doing. You start with a leaf, combine it with something to produce a higher level hash, and repeat this. Not going into the details, but this is a program, and the question is, well, could we potentially implement such a program to run inside Bitcoin scripting language? Because we don't have a native construct in Bitcoin to do so. And the fact is, we can, almost. So this is a literal translation of the program from one side to the other. Unfortunately, it requires this cat operation, which is the concatenation, which is an operation that was disabled in Bitcoin years ago, 2009 or 2010, due to fear of DOS potential. However, in Elements Alpha, our first technology demo sidechain we released, we re-enabled this opcat, and this was actually accidental. We just made a general improvement. I think Patrick over there did it. And then later realized that this actually enabled the implementation of these Merkle trees. On the right you can see what the stack is. I'm not going to the details, but if you're interested, you can go through it and see that it actually works out. So, we can use this. So, what someone would do is publish a public key, publish this path along the Merkle tree to prove that it contained results in a hash, in the root hash. Then publish a signature with that public key, and all you need to do is verify that the Merkle branch results in a hash that is equal to the root, and that the signature checks out with this public key. So we've combined the checking that the public key is member of a set, and then actually do a signature check with it. So this has very nice performance properties, because what ends up to the blockchain is just a single signature check, plus a bunch of hashes, and they are much faster to validate than a signature check. And this results in logarithmic storage size. So every layer in the tree you add doubles the number of potential keys, so we can create something with thousands or hundreds of thousands of keys and only have a few levels in the tree. Now, why would someone want 1 of n? Scheme is not typically something that's being used. So one use case is honeypots. If, say, you have a server farm with 10,000 machines and they all have a wallet, or you want to see whether someone breaks in, perhaps you want to give a certain incentive for an attacker to steal the money that's there. Now, say I have, for my 10,000 machines, I have 10 Bitcoin at my disposal that I don't care about, that I'm willing to lose if that means I can detect an intrusion. In a normal scheme, I would need to put 1 millibitcoin on every machine, and it's very unlikely that an attacker would find this interesting enough to steal. However, if you have a 1 of n multisig scheme with 10,000 keys, you can share your 10 Bitcoin all over the entire set. So every machine would have full access to those same 10 Bitcoin. And if a single machine is broken into, presumably they still steal the whole thing. And at the same time, because of this accountability property that this also has, you would know which machine was stolen. You'd give a separate key to each of them. Okay. So
how many keys?
So if
I thought you could only do 7 keys.
No, so in Bitcoin's check multisig you can, but using the approach I've just shown here, you can build a Merkle tree with 10,000 keys at the bottom, and the tree would only be 14 levels deep. So it's a few hundred bytes to do. So this is a logarithmic storage size that this approach has. because you only publish a single signature and a single public key, and then in logarithmic space can prove that it's a member of this huge set of 10,000. Okay. Any other questions about this section already?
How big is the script to do this checking?
It's 6 operations per level. So 6 bytes per level, plus you would publish 1 hash per level for the branch and 1 boolean. So it's 40 bytes that get added per level that ends up in the blockchain. So per signature, but you only do 1. Yeah, for now. Okay, next step. What can we do with, what if instead of just 1 signer, we want everyone to sign? Turns out for this there is also a solution. So I'll briefly talk about Schnorr signatures now. And those are pretty much ECDSA as it should have been. Unfortunately, Schnorr signatures were patented at the time when ECDSA was being standardized, so the world sort of settled on using ECDSA, but ECDSA is pretty much a workaround for the patent that Schnorr has. So Schnorr is faster, simpler, it has a stronger security proof, it's provably non-malleable, it supports batch validation, recovery, all properties we like to see in ECDSA, but no.
And the patents run out. Yep.
Yes, that's important. So the patent did run out, I think, in 2009. Actually, there's no reason why Bitcoin couldn't have used it from the start, except ECDSA was the standard, so let's use that. However, the reason that Schnorr signatures are interesting, they also support native multi-party signatures. And a multi-party signature is a scheme where different participants jointly construct a single signature. And this is actually exactly what we want for this K of K mechanism. How it works is, so here's an example with 4 keys. They would all produce a nonce, which is actually similar to a public key. They would publish their nonces. They'd all combine everybody's nonces into a combined nonce. Then everyone takes this nonce and uses it to produce a partial signature. And then in a second round, you would merge all these signatures together to produce a joint combined signature. And this combined signature is now valid for the sum of the public keys. So this really results in a amazingly performant multi-signature scheme, because what ends up into the blockchain is a single signature check. People don't even see how many keys were involved. So I want to send a transaction to your, and I want you 3 to sign to unlock it. So I would send my coin to the sum of your public keys. And in order for you to unlock it, you need to collaborate using this 2-round scheme I gave to produce a signature. And none of you need to reveal the private keys to each other. So this is K of K, and it does it in constant size and constant verification time. The only downside is it requires 2 rounds. Because you first need to publish the nonce, and then...
It's also order in significance. You can present the order in any order.
Sorry?
Schnorr signatures are also ordered. You don't have to have them in order, so you don't have to know what the order of the keys are, whereas in ECDSA, you have to know the order of the keys.
Right. Well, ECDSA, you only have a single key, but using a check multisig construction, you need to obey the order, and the order is irrelevant here. Yes, that's true. To combine these, maybe you can guess this now. We have one scheme that allows us to produce a Merkle tree to prove membership of a large set. And otherwise, you have a mechanism for taking several keys and making it look like a single key. So just combine these two and you create a Merkle tree where every leaf is one of the potential combinations you want to allow with different public keys. So, for example, if I would want to do a 2 out of 4 signature, this has 6 combinations. There are 2 out of 4 keys. So I've listed them here, K1, K2, K1, K3, and so on. You turn this into a Merkle tree, where in every leaf you sum up all the involved keys, take a hash of it, work your way up through the Merkle route, and you just send the coins to a Merkle branch verification plus a single signature checking. So the performance of this is it's still nearly constant validation time because there's only a single actual expensive signature check involved, though there may be several levels of hashes which are much faster. The space required for this sort of mechanism, so the amount of data this requires on the blockchain, is logarithmic in the number of combinations of keys. And the signing time is linear because during signing, you need to construct the Merkle branch, and in order to do so, you need to know the entire tree, which is unfortunate as there is a certain overhead to computing the sum of the public keys in each of the leaves. So here is a table of all up to 20 out of 20 keys. I don't know whether you can read the numbers of how many combinations exist. So for example, if I want to do the worst case is a 10 out of 20, which with 184,000 combinations. So I would construct a Merkle tree with 184,000 leaves, each of which is the sum of 10 public keys out of 20, add them together, work all the way up to compute the hash of the root, which would in this case be 26 levels. No, that's not correct. Anyway, 18. Right. Still, you need to iterate through those 184,000 combinations in order to compute the Merkle root or the Merkle branch during signing. In practice, that's 2 seconds. So yes?
With this property of summation of public keys with Schnorr, what's to stop someone from doing an attack where they forge a key by generating a whole bunch of public keys and finding a way of summing those to the attack thing that they want to do and then signing with all the ones that they generated?
Public keys have 256-bit entropy in them. So in order, it sounds like you're trying something like a collision attack, which would still have 2 to the power of 128 in order to pull off. Yeah. So
there is an attack that your implementation avoids. I don't know if we'll talk about it tonight.
I might mention it later. Try not to distract too much. So up to numbers like this is perfectly viable in most use cases, assigning time. But if you would go up to, say, 1 billion combinations, the signing time or constructing the address even requires probably several hours of computation, though it's parallelizable too. Okay, so that's a better K of n. So let's now see, we're not actually in this scheme restricted to just doing K of n, right? We are constructing a Merkle tree in which each leaf is some combination of public keys. So it's really just a means of describing a particular condition over what public keys we want to allow. And there's no reason why this policy is just limited to K of n. So came up with this idea of using a threshold tree, which is a tree structure in which you only have, every leaf in the tree is still a public key, and every inner node is some combination. It says n out of the levels below need to be satisfied. So where or is the same thing as only one has to be satisfied, and is all of them have to be satisfied, but you could easily just as well use 2 out of 3 or whatever. So the description I give here is an OR of an AND, of a threshold of an AND. And this just says either K1, K2, K3 all sign, or 2 out of K4, K5, and the combination of K6 and K7 have to sign. And you can construct arbitrarily complex descriptions like this, and this is a universal scheme. So actually any Boolean circuit, any monotonic Boolean circuit is the correct term, of conditions, all sensical, whatever, conditions you would want to allow over sets of public keys can be represented by this. Only AND and OR is sufficient, but by adding this threshold ability, K of n, into it, it's much more expressive. So this is implemented. So you can look at the source code of it. It's not yet merged into Elements Alpha, but will do so soon. So you can create such a description of AND and OR and threshold of different public keys that you want. It will compute the address for it, allow you to send to it, allow signing it, transferring the partially signed transactions for it around, and result in a valid transaction. A few interesting implementation details here are, all of it works in logarithmic space. So even if you construct have a description that results in, let's say, 1 million or 1 billion combinations, those billion combinations are actually never fully materialized in memory. How this works is it iterates over your description tree to produce one by one the different combinations in a lazy way. And then there's a Merkle root and branching algorithm that will consume these to produce a Merkle branch of a Merkle root, and never keep all of them in memory at the same time. So this means that all this code is actually can perfectly reasonably run on low power, low memory devices, which is something you usually want for multisig schemes. And it's actually tested at least once. So let's get back to the ace up properties I mentioned in the beginning. So the accountability property, can the participant see who signed off? Yes, because it's obvious from the signature, you can see which position in the tree your leaf was. And the participants in the transaction know the full tree, so they know what it corresponds to. So this is the same between check multisig and these tree signatures. Composability is obviously much more powerful. I can take 2 trees and I can combine them in arbitrary ways. That's pretty much by construction what it does. The efficiency here, check multisig has faster signing because you don't have this iterating through all combinations thing, though tree signatures have faster verification. That's really what we care about in resource constrained blockchain systems. So then there's the usability. It's similar, except tree signatures have 2 combination rounds due to the requirement that people first publish their Schnorr nonces and then combine them together, sign and combine again. And then the privacy argument, adding, if I want to hide my policy, or even better, I want to hide who is involved in the transaction, what keys are, the way to do it in all of these schemes is by adding dummy keys to it. And in Check Multisig, this is extraordinarily expensive to do because we're only limited to 15 keys entirely. Though in tree signatures, I can easily double the number of keys and only add 1 level to the tree. So then I'll show you some benchmarks. So this is a graph that shows the size of the signature in function of the number of keys that are involved. For tree signatures, the worst case is where k is half of n. So 10 out of 20, 5 out of 10. This results in the maximum number of combinations. So those are the red lines. For Check Multisig, the worst situation is where you have the number -1. So 19 out of 20, 9 out of 10, and so on. So that's the blue lines. And then the dotted lines are Check Multisig, and the full lines are tree signatures. So you can see it's always. There's actually not a single case where Check Multisig is better. I do need to point out this is a logarithmic scale in microseconds.
That's the size graph.
Oh, sorry, that's the next graph. So this is the size. So 100 kilobytes is the largest transaction that can fit in a Bitcoin block. So that's the limit. I should also add that it's not entirely honest to say the full red line goes up there, because the signing time is exponentially related to the size of the signature, and the largest one up there to compute it will probably require more computation than the universe can do in a reasonable amount of time. So it only goes up to around a kilobyte to compare. So this is a graph for the validation time of both. Check Multisig is the dotted line that goes diagonally, while the 2 lines below are tree signatures. So
yeah, that one's microseconds.
Yeah, so it's microseconds, so it goes up to 0.1 second for a validation.
No, 100 seconds.
100,000
Oh,
microseconds is 0.1 seconds, Greg.
I only made the graph, sorry.
Yes, it's microseconds.
Where's the dotted red line?
So in Check Multisig, the validation time depends on the number of public keys and not on the number of signatures. So the dotted blue line and the dotted red line coincide. Yeah. Also, again, the place where the red line visibly goes above the blue line is not interesting because it's infeasible to actually construct such large signatures. Okay, so these were threshold trees, which is what we've actually implemented. So briefly say something about future work here. A first step is all of this is implemented in Elements Alpha, our sidechain, but we had to use a sort of an emulated construct to validate Merkle trees, which is not a native feature in the scripting language. So it's slightly inefficient and more a side effect of what we can do, but it is perfectly possible to create a specific opcode in the Bitcoin scripting language, or alpha scripting language, that takes a Merkle branch and validates it. And it's interesting to see that this is actually only a soft fork. So that's something that could relatively easy be added to Bitcoin if there was demand for it. Yes.
Would it make sense to actually build this in natively so there's like paid a Merkle root of script hashes instead of just like paying a script hash?
Next point. So in addition to native Merkle branch checking, to be able to make this work into Bitcoin, we'd also need Schnorr's signature support, but that too is possible with a soft fork and would bring in several other advantages like batch validation. Batch validation is where you take a bunch of signatures and you verify whether all of them are valid or at least one of them is invalid. And there's a factor 2-3 speed up to get over a single validation. It's like exactly the thing we want in Bitcoin during block validation. So a next step, and this is actually an idea that's much older than all of this work and sort of what expired it, is Merkleized abstract syntax trees. We're not really limited to producing a single balanced tree of combinations of keys. We could, in fact, restructure the scripting language entirely to be tree-shaped, where you have and or things. You can put check a lock time, check a signature, and all sorts of complex conditions that you can write, but structure them as an abstract syntax tree, as a parsing. So you have basically just some expression that defines the condition for spending something using signature checks and whatever. Then turn this expression into a tree, like an OR of check sig A, check sig B would be a tree like I've shown. And then you put Merkleization directly onto this tree. So every node would get a hash associated with it that depends on the hash of the leaves below. And so this basically allows you to build a huge script of different conditions and only reveal the part of the script that you're actually using to satisfy. So that would be a next step. That was not something that's easy to do here, but I'm very interested in working on that. And another way of seeing this is like doing P2SH recursively. So where you pay to a hash that reveals part of a script, and part of that is again a hash which reveals a part of a script, and so on. I can, yeah. If you're interested, we can. Yes.
I'd point out with math something that might make it a little more clear to people is this big tree of signatures can be a big tree of instructions, saying if
right.
this is to return true, check these 3 keys.
Right. So it's
very, very similar ideas.
Turning the actual script into a tree rather than just the keys of it. Other work is other efficient signature schemes. So the mechanism I've presented here is very good for certain use cases, but it's not good for others. You cannot do 50 out of 100 here due to the combinatorial explosion of combinations of 10 out of 100. So even though the signature would, in theory, be small and the validation time would be small, it's just completely infeasible to sign this. So there's other work that Greg refers to in the talk I should have linked to, but you didn't see, such as a Multisig, which is a mechanism that's very efficient for k of n, where k is really close to n. Or if you don't care about the accountability property. If you don't care about seeing who signed, there is ring signatures, which have similar compact representations. So, thank you for your attention. More questions? Yes?
Once you've calculated a complicated tree, is there a way to reuse the root for multiple payments?
Yes.
Is it safe to just use it directly, or do you want to somehow promote it so it's not recognized that the payments are going to the same place each time?
Well, ideally, you would never reuse a single key in the first place. And if you care about this sort of privacy, which you should, then it's a non-issue because you'll be using new keys anyway. However, it is true that what you can do is just have a single dummy key which does not have a corresponding public key involved, and anytime you reuse it, you change the dummy, so it's not recognizable that it's the same, only due to the path somehow being similar. So you get some advantage. Yes?
Okay, so when you mentioned the other efficient signature schemes, what about the one that's like threshold signatures from Princeton? You may have meant that when you said Multisig.
I don't think I did. But Greg probably knows more? Or?
That's referring to the ECDSA stuff. So the problem with the existing ECDSA efficient signature schemes is they require many round trips to complete. And we think this is like less exciting because it makes it very hard to build useful applications out of them.
More than two?
Yeah. Yeah, more than, really when you have to go round trip multiple times, like you have 6 devices and you have to visit each one 6 times. If they're in safes, you're about to shoot yourself,
it's
right?
Like, tap your phone again, tap your phone again, tap your phone again.
But with a 10-minute wait as someone else taps their phone, right?
And I also want to be clear that, I mean, for the Bitcoin blockchain, it's ECDSA, but there are other blockchains. I mean, Eris can be configured for 25519, which is a Schnorr signature native.
Mm-hmm.
So there are other blockchains that.
But I think 25519
It's a curve, so it
does not support adding public keys together or something because it has a requirement on particular bits being set.
There's curve and there's
Yes.
ECDSA. So
There's add 25519 in curve.
But this works. This will work in Bitcoin eventually. This is a trivial software.
Oh no,
So
I'm just saying.
it just yeah.
This isn't just useful for Bitcoin. It's useful for a lot of other blockchains.
Yeah, so the question was about another signature scheme called add 25519.
Curve 25519 breaks hierarchical wallets. That's the thing that really.
Yeah, that breaks this too. Yeah, it breaks the addition. At least with standard implementations, the curve is fine. The implementation.
Yes.
So thanks so much for the presentation. This is somewhat unrelated, but as I was looking at the graph showing the time it took to validate a check multisig operation, has there ever been simulations done to see if you filled a block as it exists today with check multisig in maximum case, how long that verification would take?
So you would fail.
Oh, really?
Because there is a limit in Bitcoin.
Well, 100 kilobytes, right?
No, there's another one.
There's a SIGOP limit.
Oh, okay.
So there's a limit in Bitcoin that limits a single block to at most perform 20,000 signature checking operations.
Gotcha.
However, this is computed in an inefficient way. So a 1 of 20 multisig, which can go up to 20 signature checks, will always be counted as 20. So you can only do 1,000 maximum size check multisigs in a Bitcoin block.
Okay. Thanks.
Yeah.
Why was CAP taken out or deactivated on the main chain, and why are those problems relevant on the side chain?
Good question.
Yes. Imagine a script: push a byte, dup cat, dup cat. This blows up your memory usage in an exponential way. you take the 1 byte, you duplicate it, you have 2 arguments of 1 byte, you concatenate together, it's 2 bytes now. Duplicate it 2 times 2 bytes, cat them together, 4 bytes. So this was a time in Bitcoin when there were several vulnerabilities being discovered, and presumably at the time they were disabled for a temporary. This restriction on disabling the cat opcode was intended to be temporary, except it now requires a hard fork to
expediency.
Well, there was an attack that you could cause many, many petabytes of memory usage in the system. And it was a real attack. No one exploited it, but it existed. So the opcode was disabled to be sure there was no attack.
So now the obvious question becomes, so why did we re-enable it? The thing is, it's size limited. So any cat that would result in a size over 520 bytes, which is the usual size limit for script elements, would fail. So we re-enabled it in a trivial and safe way. Which I'm sure people could have done in Bitcoin at the time too, but nobody bothered.
It took work. It would take work to check to make sure that that fix was sufficient. And when you have a production system that's in danger of being damaged by it, you don't want to spend a lot of time to figure out if the fix is sufficient. But for Elements
also,
Alpha,
there were no use cases for it, as far as I know. This is one of the first use cases for the Katz instruction. I'm sure we would have found others if it was enabled. But any other questions? Yeah.
Just talk about some of the use cases for having a multi-signature contract with many, many signatures, so beyond what Bitcoin currently.
repeat the question.
So the question is, what use cases would there be for having many, many keys in a multisig? So I mentioned one, the one of honeypots, but mostly this is not really about having that many keys. It's just the number of combinations that blows up, even with not that many keys. What other use cases would there be for moderately large? Some mechanism where you need a majority out of a bunch of people to agree, and you want them to all have their own keys. I mean, there's no way you can do
stock voting. Stock voting.
Stock voting.
Yeah, there's 5,000 shareholders and 4,000 of them will let the board.
Yeah.
I did have a client who wanted that implemented. So there's people willing to pay money for that.
There you go.
I'll pay.
Yeah.
Can you give some examples of where it would be advantageous to use that sort of Merkle tree structure to create a script instead of using a snap?
So there is it is advantageous whenever you don't want to reveal the entire script, and this is actually something that's pretty useful. So imagine we set up some complex smart contract that pays out using different criteria and whatever. So this would be a large signature to satisfy, presumably. However, using this tree structure, you can create something that's just an OR of either this complex or the end of both of us. Whenever both of us just agree, yes, the rules are satisfied, we don't need to prove to the world that it was satisfied, we just agree. So in that case, the entire section of the complex smart contract would not end up on the blockchain at all. So you would just send to the root hash of the script, and we would just reveal the left branch. Yep, we agree, simple to multisig.
Thanks.
So just to be clear, the right side, which is the complex contract, where would that be then? On a sidechain?
No. This is completely independent of what blockchain technology we're using. The tree is only conceptual. Like we jointly construct this tree that describes the conditions under which things get spent. And whenever we sign coins away, we reveal the part of the tree that we need. And given that there's a branch...
Okay, so there would be a smart contract system that's its own implementation.
Well, the smart contract could just be a complex combination of multisig that does a check lock time. There are various extensions that could be enabled here. Yes, I'm being asked to repeat the question when
Sorry, guys.
Okay.
Any more questions?
He's got to have something to repeat.
What's your slide software?
Yeah, that's made using Prezi.
What?
Prezi.com.
It's a Flash thing.
It zooms.
Okay.
It's awesome.
It's
Flash.
Also, there's a blog post about this, so you can read it more calmly.
So did you want to talk about that vulnerability, that attack that you...
So
Repeat the question.
the question is whether I would want to talk about the vulnerability that was potentially avoided here, and the answer is yes. One of the problems involved here is if you have several people distributing their keys to jointly construct. So we want to do a 3 of 3 multisig. You give me a key, you give me a key. And say, hey guys, my key is the sum of the negation of your keys. So what the scheme would do is compute the sum of those 3, and my key would cancel out your key. So in the resulting public key, only his is left. If my public key is the negation of yours, and we create the sum of the 3 of them, which is what you do at the leaves of the Merkle Merkle tree, would be A, B, minus B, so it sums up to A, and the result is that just drag and sign for the 3 of us.
I like this plan.
So the solution to avoid this is whenever these nonces are being published, the nonces themselves are being signed by the keys involved. So everyone can see that everyone else actually has the ability to sign for their own plain public key.
You spoil sport.
Sorry?
I said you spoil sport.
Yeah. I'm sure.
Any more questions?
What do you think of the hard fork?
The question was whether there were any more questions.
The answer is...
Yeah, the answer is apparently yes. Sorry, I didn't hear.
I said, what do you think of the hard fork? Never mind.
Repeat the question.
What do I think about hard fork? I think we should very hard try to avoid controversial hard forks. I think we should work towards a solution that the whole entire ecosystem can work on. That's also... That's also what the workshop is about. So.